So annoyingly, I paused the video there. I'll just carry this on straight away. So the thing to do with this one is to write out the equation for Kc, which is the concentration of C raised to its power of the coefficient of the reaction over A to the 1 and B concentration squared. We're given the concentrations in the question, so it's 2 squared divided by A is 2 and B is 1 squared. That comes to 4 divided by 2, which is equal to 2, which is C. Question 31, which reaction would be expected to have the highest Arrhenius factor? Again, let me just pause and have a think. Right, so the pre-exponential factor in the Arrhenius equation is all to do with the orientations and frequency of the collision. So essentially here we've got to think about the orientations. Now for two reactants to collide and cause a reaction, they need to be in the correct orientation. And I've shown you some examples of this, and we've been doing organic chemistry. So the molecules have to approach, for example, from behind the bond to go into an anti-bonding orbit, all that kind of stuff, a bit beyond what you need to know. But you do need to know that orientation is important. But because the atoms in A, or the substances, the reactants in A, are such simple molecules, simple atoms rather than molecules, it doesn't matter what the orientation is, it's irrelevant. So they're going to have the highest pre-exponential factor, and that is the answer. Okay, so you are expected to, the thing you're expected to know here is the pre-exponential factor to do with orientation of the collisions. And for this one, it won't matter. Which reactions involve the transfer of a proton? Let's have a look at these one at a time. So this one is clearly a redox reaction where the magnesium's gone from 0 to +2 and the hydrogen here has gone from +1 to 0, so that's a redox in that one. This one's a straightforward acid-base reaction, as you learned in year 10. We've got magnesium oxide base reacting with hydrochloric acid to give the salt and water. Likewise, another acid-base reaction, so magnesium carbonate this time rather than oxide, and so that is, so C is the answer there. Question 33, we've got an indicator H in, so nearly always indicators are weak acids, and when the weak acid dissociates into its two individual ions, the weak acid and its conjugate base have different colours to each other, so you can detect them in different pHs. Right, so let's work through each of these possibilities in turn. So if we've got an alkaline solution, when we make an alkaline solution, colour B is observed. So in an alkaline solution, you need to think of this from the perspective of Le Chatelier. So an alkaline solution has got high pH, you've got hydroxyl ions present, they will react with the H+, remove it from the reaction, the equilibrium will shift to the right, forcing the Ind- to form, so colour B will be formed. So in strongly alkaline, colour B will form. Colour A is observed when the concentration of that is less than the concentration of that. Well, if the concentration of Ind- is higher, you'd expect to see the concentration, the colour of that, which is B. So no, that ain't right, is it? And at the end point, that's the point at which you're sharply changing pH, the concentration of both of them is about the same. Yeah. And that's 1 and 3, which is B. So what does that make sense, that last thing? So we remember that we choose our indicator to have a pK in, or a Kc if you like, or Ka, whatever you want to call it, for that reaction should be about the same pH at which the acid-base titration finishes, and that means you're going to have a 50-50 mix roughly at the end point. That's the point at which you get the sharp change in pH. Question 34. You've got here a reaction occurring at the electrodes of a rechargeable metal hydride battery. A couple of questions about batteries that can be summarised as the following. Which statement is correct? So the nickel here, we can just work out the oxidation states. I'm just going to do that and then write them above. So the nickel here, you've got each oxygen's -2 as always, the hydrogen's +1 as nearly always, and so the nickel have to be +3 there to make sense. Nickel's gone from +3 to +2, so that ain't right because it does change oxidation number. There's no loss of hydrogen. I see, so the metal is oxidized by the loss of hydrogen, right? So the metal here is 0, and the metal here is, I don't know if you remember, metal hydrides are plus. The metal must be plus, and the hydrogen in metal hydrides is -1. So the metal here is being reduced, so it ain't that. Oxidation state of the hydrogen changes from -1, and it'll be +1 over here. Yep, that's right. And the oxidation state of oxygen doesn't change in this reaction at all, so it's not that. It's all about remembering that metal hydrides are -1, and every other situation, hydrogen, well, unless it's an element, which when it's 0, is always +1. Question 35. In a redox titration, manganate ions are reduced to manganese 2, so that's a 5 electron change, and iron 2 are oxidized to iron 3, that's a 1 electron change. What volume is required to reach the equivalence point in titration of 20 of those? So the number of moles of Fe2 plus is 0.02 decimeters cubed times by 0.1 is equal to 0.002 moles. So that's the number of moles of Fe2 plus. You divide that by 5 to work out the number of moles of the manganate needed, because each one's giving away 5 electrons. Just realise that the concentrations of the two ions are the same. So all you've got to do is realise you've got to divide that volume by 5 to give 35 as B4. Okay. So you need a fifth of the volume of that stuff as that stuff, because it's a 5 electron change, +7 to +2, +2 to +3. Question 36. Can you explain these things in the atmosphere? Right, the reason that they break down, chlorofluorocarbons, is because the carbon-chlorine bond is weak, easily broken by UV, and so it had to be one of the ones that says that Cl is weaker. So it had to be either B or D. And then you've got a chain propagation steps to produce more radicals. That makes no sense. This chain termination step will stop the formation of them. Let's just remind you of the reaction there. So first thing is the CFC breaks down to give Cl plus. Just like, so if I just draw a CFC, if we go RCl, the UV will cause that bond to break in the same way that in the first step of the free radical substitution reaction. Cl dot can react with O3 to give ClO dot plus O2. ClO dot reacts with another molecule of O3 to give 2O2 plus Cl dots as a propagation. Propagation 1, propagation 2, you spit out Cl dot from the second reaction, and 2 molecules of O3 turn into 3 molecules of O2. If we've not covered that recently, quite happy to go through that in class with you. Just to be clear there, the answer was D. Which term cannot characterise ammonia? Cannot characterise it. So let's start off by just reminding ourselves what NH3 is. It's got a lone pair there, and it can act as a nucleophile, right? So lone nucleophiles are things that can donate pairs of electrons. So it ain't that it can act as a ligand, can't it? Because you can have ammonia ligands forming coordinate bonds to transition metals, for example. Lewis acid, it certainly is not, it's a Lewis base. So Lewis bases can donate pairs of electrons, Lewis acids accept them. So that is the answer. Bronsted-Lowry acid, pretty unusual, you've never seen this quite possibly, but you can, this can act as a base, at least theoretically, to give this thing here, okay? It's a pretty crappy acid, to be honest. Which ion is a better leaving group? So big ions are good leaving groups, so D is the answer there because that's the biggest ion. So a fact you need to know. Question 39, which statement is correct when 2-chloro, 2-methylpentane, 1, 2, 3, 4, 5, 2-chloro, 2-methylpentane reacts with water? So you've got to then know that that's a tertiary halogenoalkane. You've got to know then that it goes via an SN1 mechanism, and if it goes for an SN1 mechanism, a carbocation must be formed, and that carbocation can form 1, 2, 3, 4, 5. That carbocation can form because you've got 2 electron, in fact 3 electron releasing alkyl groups around that cation. So that is the answer. Water does end up reacting with the carbocation as a nucleophile, but it doesn't attack the chlorine atom. It's a 2-step reaction, so it ain't that. And homolytic bond fission occurs. No, it's heterolytic, isn't it? So it ain't any of those. Last one, everybody, I think, got it right. About, well, I think everybody did. And it was A. We've done that pretty recently. That's the intermediate. Done.